Thank you very much for your nice introduction. It is indeed a great pleasure to be here, and I'm very happy to be in this beautiful city. And I'm going to talk for about 1 hour. That is the time allotted to me, and I hope I don't exceed that. Dr. Roy, you please tell me 5 minutes before so that I can quickly conclude. Or else what I will do is I will start looking at the audience. When they slowly start leaving, then that is that's a good time to stop. Once again, thank you very much for this very kind invitation. I'm indeed very happy to be here, and it seems the next Prime Minister is probably going to. Is this getting recorded? Oh my God. So let me come to the subject myself straight away. So I have to be careful in what I say. So Albert Einstein and his year of miracles. So in 1999, before the century ended, you see, in India we have all the time who is the Indian of the year, and we usually give the Indian of the Year award to people like Sachin Tendulkar and Amitabh Bachchan and others. So in 1999, the famous American Time magazine wanted the name of the person, wanted to select a person who has made the greatest contribution to humanity for the whole 100 years, from 1900 to 1999. A person who has impacted the lives of humanity at large. And there were, as you could imagine, hundreds of nominations, from John Kennedy to Marilyn Monroe to Winston Churchill to Mahatma Gandhi to Mother Teresa and many others. Hundreds of nominations came in. And eventually they had to select, they had to have a selection procedure, and they chose there were three finalists. And the three finalists were Franklin Roosevelt for triumph of freedom over fascism and communism. In the December 31, 1999 issue, the last issue of the previous century, Bill Clinton wrote about Roosevelt, and read this: when our children's children read the story of the 20th century, they will see that above all it is the story of freedom's triumph, the victory of democracy over fascism, of tolerance over prejudice. Prejudice is again, what he meant was against the color. We have also prejudice in our country, so we have to be careful. So the victory of democracy over fascism, of tolerance over prejudice, and they will see that the embodiment of that triumph was President Franklin Delano Roosevelt. The other finalist was Mahatma Gandhi, as the embodiment of human rights and his faith in non-violence. And the quotation John McGarry wrote in the same issue of Time magazine, of which I happen to have a copy, in an age of empire and military might, Mahatma Gandhi proved that the powerless had power, and that the force of arms would not forever prevail against force of spirit. Our passionate commitment, non-violent activism, willingness to accept punishment for civil disobedience were lessons that Mahatma Gandhi taught. Martin Luther King learned them, so did Nelson Mandela, Lech Walesa, Aung San Suu Kyi, the unknown Chinese who defied the tanks in 1989. And read the last line. Gandhi is that rare great man held in universal esteem, a figure lifted from history to moral icon. But the person who was awarded the Person of the Century award was Albert Einstein. He was chosen as the Person of the Century. And in the same issue of Time magazine, Frederick Golden wrote, Einstein was the preeminent scientist in a century dominated by science. The touchstones of the era, the atom bomb, the Big Bang, quantum physics and electronics, all bear his imprint. He was the embodiment of pure intellect. He was unfathomably profound. The genius among geniuses who discovered merely by thinking about it that the universe was not as it seemed. I started at 7:15, so it should be over by 8:50. He was born on 14th March 1879 in a southern town of Germany by the name of Ulm. Many people believe that he was not a very good student. He was a very good student. In fact, this is his school leaving certificate when he was about 17 years old, which shows, if you read this, if you see this, that he scored the highest grade in physics, algebra, geometry and history. So he was all the time a very, very committed student, he got very good grades, but he disliked the German and the Swiss education system. He studied when he was about 17 to 21, about the time you go to college here. He studied in this technical high school, Hochschule, in Zurich, and at much later date, he also worked here for a while. About the educational system in this institute, and this is very important for people like us, teachers and lawmakers, that about the examinations in this institute, Einstein later wrote, one had to cram all this stuff into one's mind for the examinations, whether one liked it or not. This coercion, this forcefully you have to learn something, had such a deterring effect upon me that after I had passed the examination, I found the consideration for any scientific problems distasteful to me for 1 year, for an entire year. So he graduated from this institute in the year 1900, and then he started looking for job, and he could not get a job. Eventually in 1902, he landed up in the Swiss patent office. And there, in the year 1905, working in total isolation, not in a university, not in a research laboratory, but in the patent office where he had a lot of free time to study. There he published 5 outstanding papers. And these 5 papers are often referred to as the Annus Mirabilis papers. Annus Mirabilis are Latin words meaning miracle year, and therefore the year 1905 is usually referred to as the year of miracles for Albert Einstein. The 5 papers that he wrote were, the first one was he described a method for measuring molecular dimensions. What is the size of water molecule? So he suggested an experiment, a beautiful experiment, to measure to get an idea of the dimensions of the atoms and molecules. The second paper was in which he put forward that light, when it is emitted or it is received, it is always in packets of energy. These packets of energy are referred to as quanta, which later came to be known as photons. The third paper was that when you take a bottle of water or a glass of water, then the water molecules are moving at random because of thermal motion. This thermal motion is very difficult to observe because water molecules are tiny. But if you put a small particle, small microbe or a virus, then because other molecules hit them, so this tiny particle moves around. This movement, this random movement is known as Brownian motion. And he gave a very beautiful theory of Brownian motion, and this forms today the backbone of what is new field of statistical physics. And the fourth paper was on special theory of relativity, which I will describe, and in the fifth paper he derived the equation E is equal to mc square. People say that each one of these papers is worth a Nobel Prize, although he had great difficulty in getting the Nobel Prize, and he got the Nobel Prize in 1922. He got the 1921 Nobel Prize in 1922. So there is a very beautiful book, and the title of the book, read the title, Einstein's Miraculous Year, 5 papers that changed the face of physics. 5 papers that changed the face of physics. It's edited by John Stachel, published by Princeton University. In the foreword of this book, the famous physicist Roger Penrose writes, "In the 20th century, we have been greatly privileged to witness 2 major revolutions. We have come to use the term relativity to encompass the first of these revolutions and quantum theory to encompass the second. It is particularly remarkable that a single physicist, Albert Einstein, had such extraordinary deep perceptions of the workings of nature that he laid foundation stones for both of these 20th century revolutions in the single year of 1905. That is, there are 2 great revolutions that has taken place in the last century. One was the theory of relativity and the other was the theory of the quantum mechanics. The basic papers for both these revolutions were put forward by Einstein in the single year of 1905. The other great scientist, as you will always say, was Isaac Newton. Isaac Newton's Annus Mirabilis, the year of miracles, was 1666, when he was only 23 years old. In 18 incredible months, Isaac Newton wrote down his famous laws of motion, explained the laws of gravity, discovered calculus, and developed a theory of optics. So Einstein also made remarkable contribution to that. And I must tell you one more thing, that in the year 1666 there was plague in the United Kingdom, and Cambridge University, where he was teaching, shut down. So he was sent back home, and there in total isolation, focus and total concentration, he produced the basic thing of the great manuscript he wrote. A major portion of the manuscript that he wrote was Principia. So what I am trying to say is, you do not require, the younger generation, you do not require great buildings or great atmosphere to do that. If you work on your own, you still can do wonders. And the 2 greatest examples were Isaac Newton and Albert Einstein. But as I was mentioning a while ago, but there is a difference between the 2 scientists. There is a difference between the 2 scientists. Isaac Newton was a great scientist, Albert Einstein was a great scientist. But the difference is, one was a much greater human being, and that was Einstein. People say that Einstein was a much greater human being. And we all should strive not only to achieve, but also to become good human beings. And in that, Einstein was loved and respected by all. On the other hand, Newton was feared by everyone. Everyone feared Newton. And that is the difference. And Einstein did not have any greed for any material things. In 1945, when he had emigrated to the United States, someone said that you rewrite your relativity paper. The relativity paper was in his house in Germany, which was burned down by the Nazi Germany. So he took the printed paper and he copied it with his own hand in German. And that manuscript was auctioned. And it was auctioned for $5 million. And he gave the entire money. He did not keep even 1 cent with him. He gave the entire money to the United States government to fight the war. So he did not own a car. He had no, and he would wear the simplest of the dress. So that is the difference between Isaac Newton. Although Einstein also had his own share of faults and things like that, but he was widely respected and greatly loved by people surrounding him. I will start with the 5th paper. I will start with the 5th paper because you ask anyone what was the famous thing that Einstein did, and most of the non-physicists will say E is equal to mc square. So in his 5th paper in 1905, Einstein developed the famous equation E is equal to, this is in Einstein's own handwriting. And what does this equation say? Equivalence of mass and energy. And that mass can be converted to energy and vice versa. And that is what this equation implies. So the simplest model of the atom, and as Dr. Anil Roy mentioned some time back, that this is the centenary of the Niels Bohr's famous paper giving the model of the atom. What is the simplest atom? The hydrogen atom. What does the hydrogen atom consist of? A proton and an electron. And in the model that was suggested by Niels Bohr, that proton is sitting at the center and the electron is rotating in a circular orbit. The different energy states of hydrogen atom, it rotates in different discrete orbits. When an electron goes from a higher state to a lower state, it loses a certain amount of energy. The atom still consists of one proton and one electron, whose masses we exactly know. But in the process, since it has lost a certain amount of energy, the mass will become smaller. So that is what he wrote to his friend after he published that paper. Light carries mass with it. This is a phenomenal concept. Light carries mass with it. So the hydrogen atom emits radiation. The quantity of matter is still the same. It still consists of one proton and one electron. But in the process, it has lost the energy, some energy, and therefore its mass must become smaller. So let me tell you. Let me give you a very simple derivation. Very simple derivation of E is equal to mc square. And the derivation is that, let us suppose you must have seen this in a railway station. You are standing on a platform, and if a train comes in, if an engine whistles, then when you hear the frequency, as it approaches, it is slightly larger. And as it goes away from me, the frequency becomes slightly smaller. And this is known as the Doppler effect. Doppler effect. And I show this through an animation that I downloaded from the internet. This is the source of light or source of sound waves. So if I am standing here, as you can see from the diagram itself, the frequency is larger. If I am standing here, the atom is moving away from me, the frequency is smaller. And in fact, these days, the policeman usually holds a device which emits electromagnetic waves, and it hits your car, and when it is reflected, its frequency is slightly changed, and by measuring the difference in the frequency, you can find out the velocity, the speed of the car, and he ends up giving you a ticket, or whatever it is. So because of that, our galaxy is expanding. Our galaxy is expanding. How do we know that? Because we measure most of the galaxy consists of hydrogen atoms, and this is the hydrogen atom spectrum. As you observe on the Earth, you find that the lines are the same, but they are slightly shifted. This is known as the Doppler shift of spectral lines. This is known as by measuring the difference in the frequency, you can find out the velocity with which the star is moving away from me. And this is the experimental basis by which we can say that the galaxy is expanding. That is, the stars are moving away from us. So, as was pointed out by Einstein, that light consists of discrete quanta. These quanta are known as photons. The energy of each photon is proportional to the frequency, h nu. Nu is the frequency, h is a constant which is known as a Planck's constant. The momentum is also proportional to the frequency. The momentum is also proportional to the frequency, and as you all know, this is equal to h nu by c, where c is the velocity of light in free space. It has a value of 300,000 meters per second, 300,000 kilometers per second. Now, consider this experiment. Consider this experiment. I am inside a train and you are in the platform. Now, there is an atom which is sitting on the table on a train, which is sitting at rest. It emits two photons of the same energy. So, the change in the energy of the atom, as I see in my frame of reference, is given by 2h nu naught. It emits two photons of the same frequency in opposite direction. Now, because the two photons have the same frequency, they carry the same momentum, and so therefore the net change in the momentum is zero, because they are two in opposite directions, and so therefore the atom which was at rest will continue to remain at rest. with respect to me. And with respect to you, the atom which was moving with a certain velocity before emission will move with the same velocity after emission. I hope you understand. So you see, with respect to me who is inside the car, one photon has this momentum, the other momentum has the same equal and opposite momentum. So the change in momentum is zero. So the atom will remain at rest even after emission from the law of conservation of momentum. And so with respect to you, it will move with the same velocity before and after emission. I hope I have done. Now you want to make a measurement of frequency. So what you do is, on the railway track, you put one person here and one person here. For her, इसको बाद में ही सर्व करना, ठीक है? थैंक यू. इसमें you have to focus. फोकस के बगैर कुछ नहीं होगा. Even next time what will happen, I will say that oh मैं भी एक ले लूँ, तो फोकस नहीं रहेगा. So I'm sorry you have. Is it all right, Doctor? तो बाद में मैं भी खाना चाहूँगा, तो वो एकदम unless you concentrate, unless you focus, you cannot do a good job. तो वो सामने जब रहेगा ना, so what will happen is that you have two observers, one in front, one in the back. So you see, for A2, she sees the atom moving towards her, and for A1 the atom is moving away from her. So she will receive a higher frequency, where u is the velocity of train, and she will observe a lower frequency. So therefore the momentum of this photon is greater than the magnitude of the momentum of this photon is greater than this photon. And so therefore if I want to now conserve momentum, so the energy change, as you will observe, will be h nu 1 plus h nu 2, and if you do a simple algebra, then you will get this expression. Now once again, therefore this is the momentum before the emission. After the emission, two photons are emitted, one h nu 2 by c minus h nu 1 by c. This is greater than this because of Doppler shift, and therefore the emission of the photons, its mass must decrease. Its mass, if the mass had not decreased, then this would have been zero, but this is greater than this, so therefore its mass must decrease. So therefore you get, in your frame of reference, if you do the little algebra, use these expressions for the Doppler shifted frequencies, you will get the change in the mass is equal to u multiplied by u will be equal to this expression multiplied by u by c square. But just the slide before this, I had shown that the change in the energy in your frame of reference will be h nu 1 plus h nu 2, and if you add this together, you will get this. So therefore, we have shown, and it is simple, that you have an atom which is moving before and after the emission with the same velocity. So it emits two photons, and you see this photon has a greater momentum than this photon. So to conserve the momentum, although the velocity of the atom is the same, its mass must decrease. So this change in the mass is so much, but I have just now shown that the change in the energy is so much. So this quantity is the change in the energy. So you get this. This is valid for all velocities. So u cancel out and you get this famous equation. This is, I have given you a rigorously correct derivation of the Einstein's mass energy relation. So change in energy is equal to change in mass times c square. So this is one of the examples. If you have two magnets with the north pole facing the south pole, let us suppose two magnets weigh 1 kilo each. Now you put on a frictionless table, they will attract each other. When they meet, it will not weigh 2 kilos, it will weigh 1.9999 kilos. Because to separate them, you will require a certain amount of energy. And thereby, when you separate them, you will, certain amount of energy will get transformed into mass. Will get transformed. When you close the fridge door, when you open the fridge door, so you will have, so when you close it, the mass will become slightly smaller. Because in order to open it, you have to apply a certain amount of energy. So energy has mass, and mass has energy. Our sun is emitting a phenomenal amount of light. It's like a light bulb, which is the light bulb power is, this is for example a 1000 watt bulb. It has 4 into 10 to the power of 26 watts. That is 4 into 10 to the power of 26 joules of energy is emitted per second. And therefore, is the mass decreasing? The answer is yes. If you use the Einstein mass energy relation, then in each second, about change in energy is 4 into 10 to the power of 26 joules per second divided by c square. So it comes out to be 4 billion kilograms per second. So thus every year 120,000 trillion kilograms of mass is continuously getting converted into energy. So is it contracting? Is it contracting? The answer is actually no. Eventually, although the change in the mass is very small compared to the mass itself, so eventually what will happen when it has spent all the hydrogen, the gravity will not be able to hold together. So sun will expand and will become what is known as a red giant and will envelop the whole earth, and life will cease to exist on this earth. And that is going to happen. That is what the astrophysicists tell us, in about a few billion years. Then life will not exist. So in his 1905 paper, this is the English translation of his German paper, and read this. If a body emits the energy E in the form of radiation, radiation is light, its mass decreases by E by c square. The mass of a body is a measure of its energy content. He wrote to his friend Conrad Habit in the same year. Light carries mass with it. He himself did not believe this argument. The argument is amusing and seductive, but for all I know, the Lord might be laughing over it and leading me around the nose. So you see, you take two particles, proton and neutron, and you form what is known as the deuteron nucleus, and you separate them. So the proton and neutron stuck together, attracted together by nuclear forces, will weigh slightly less, because you have to pump in certain amount of energy to pull them apart. And this is known as the mass defect. This is known as the mass defect. Okay. So this is a typical fusion reaction in which you have deuteron, which consists of proton and neutron, and a tritium. They fuse together and they form a neutron and an alpha particle, which consists of 2 protons and 2 neutrons. You see here also there are 3 neutrons and 2 protons, and final product also 3 neutrons and 2 protons. But alpha particle is a very tightly bound nucleus. It has a lot of binding energy. And so therefore a small amount of mass gets converted into energy. And in this particular example, light is not emitted. The energy is in the form of kinetic energy, in the form of heat of the 2 particles. But here also, a small amount of mass gets converted to energy. So, if you ask me the question, that if you burn a piece of paper, if you burn coke, then light is emitted. Is there a loss of mass? Of course there is a loss of mass. But that mass that is lost is so small that it is very, very difficult to measure. So Einstein says, this is Einstein's own words in 1934. And read this. It followed from the special theory of relativity that mass and energy are both but different manifestations of the same thing. A somewhat unfamiliar conception for the average mind. Furthermore, the equation E is equal to mc square, in which energy is put equal to mass multiplied by the square of the velocity of light, showed that very small amount of mass may be converted into a very large amount of energy and vice versa. So I will If you hear the original voice of Einstein, some of you may have heard this.
It follows from the special theory of relativity that mass and energy are but different manifestations of the same thing, a somewhat unfamiliar conception for the average man. Furthermore, the equation E is equal mc squared, in which energy is just equal to mass multiplied with the square of the velocity of light, shows that very small amount of mass may be converted into a very large amount of energy, and vice versa. The mass and energy were in fact equivalent, according to the formula mentioned above. This was demonstrated by Ghatak and Walton in 1932 experiment.
This is a very important thing to see, that although it was predicted in 1905, it could be confirmed only in 1932, for which Ghatak and Walton received the Nobel Prize. But as I mentioned, even if you burn a piece of paper, then also you will have a certain amount of mass getting converted to energy, but that measurement is extremely difficult. So it required nuclear reactions to appear, and those were there. Therefore, the E is equal to mc square was verified experimentally in mid-30s. But he was never given the Nobel Prize for this equation. And as you all know, when a neutron hits an uranium nucleus, then what happens is the neutron gets bound to the uranium nucleus, as you must have read in your high school, and then it starts vibrating. And in this process, it becomes like a dumbbell. It becomes like a dumbbell and splits into two smaller nuclei. And we say, and this is what Lise Meitner had said, the fission has occurred. The fission of the uranium to the breaking up into two smaller parts. But these smaller fission fragments are very tightly bound. So a small amount of mass gets converted into energy, into a large amount of energy, and that is how you obtain a large amount of energy in a fission reaction. A controlled fission reaction is a nuclear reactor, and an uncontrolled nuclear reaction is an atomic bomb. So as soon as this was discovered in 1938, and in 1939 the World War II had started. This was discovered by Otto Hahn and Lise Meitner. There's a long story, I do not have the time to do that, but Lise Meitner was actually the discoverer of the fission process, although the experiment was first carried out by Otto Hahn, and he got the Nobel Prize for that. And then in this process, one found out that there are 2 or 3 neutrons that are also emitted. So immediately one could figure out that there could be a chain reaction releasing in a large amount of energy. And therefore, by that time Einstein had moved to United States, and since Germany was trying to occupy most of Europe, and since the discovery of fission process was in Germany, they feared that the Germans will be the first to make the atom bomb. So in August 1939, Einstein wrote a letter to President Roosevelt. It said that United States should start working on nuclear weapons. And the first reactor, as you would know, was made by Enrico Fermi in 1942, and then Robert Oppenheimer was made the director of the Manhattan Project for building the atomic bomb. And then Robert Oppenheimer was a theoretical physicist. He was a great physicist. Many people feel that he should have also received the Nobel Prize. And the first atomic bomb was exploded in a city in New Mexico on July 16, 1945. And when he saw this awesome explosion, when Oppenheimer saw this awesome explosion, he said, "I am become death, the destroyer of worlds." Actually, he quoted from Bhagavad Gita, when Krishna is telling Arjun that I am all devouring death and the prosperity of those who are to be prosperous. I am fame, prosperity, speech, memory, intelligence, firmness, and forgiveness. Robert Oppenheimer remembered almost the entire Bhagavad Gita by heart. So when he saw the atomic explosion, he said, "I am become death, the destroyer of worlds." So years later, Oppenheimer had said, "We knew the world would not be the same. A few people laughed, a few people cried, most people were silent. I remembered the lines from the Hindu scripture, the Bhagavad Gita. Vishnu, he actually erroneously says Vishnu, it is actually Krishna. Krishna is trying to persuade the prince, there is Arjuna, that he should do his duty, and to impress him, takes on his multi-armed form and says, now I am become death, the destroyer of worlds. I suppose we all thought one way or the other. So I will show you, I will make you hear another small video. It's a beautiful video.
5, 4, 3.
Oh, sorry.
5, 4, 3, 2, 1.
This is the first atomic explosion on July 16, 1945. See the awesome explosion.
In the dead silence of the morning, at 5:29:45 Mountain War time, the Jornada del Muerto was bathed in an intense flash of a light that man had only seen from the stars.
See what he has, you just listen, that man could see light that only could be seen from the stars. Man had created the light that could and energy that could be only generated in stars. New Mexico. And the next voice is that of Oppenheimer. This is the light coming from that explosion. Listen to it.
The world would not be the same. Few people laughed. Few people cried. Most people were silent. I remembered the line from the Hindu scripture, the Bhagavad Gita. Vishnu is trying to persuade the prince that he should do his duty, and to impress him takes on his multi-armed form and says, now I am become death, the destroyer of worlds. I suppose we all thought that one way or another.
So immediately after that, as you all know, the uranium bomb was dropped on Hiroshima and the plutonium bomb was dropped on Nagasaki. 6 months later, Einstein's photo came on the painting came on the cover of the Time magazine, and if you can see, E is equal to mc square is written and a mushrooming cloud of explosion. If you read this article, if you read this Time magazine, you will feel that probably Einstein was the father of the atom bomb. Contrary to popular belief, Einstein did not play any role in the Manhattan Project for building the atom bomb. Einstein's two main contributions were his famous mass energy equation, on which is the basis for the liberation of so much amount of energy, and the letter that he wrote to President Roosevelt recommending US research on nuclear weapons. Einstein learned of the atomic bombing of Hiroshima through the public announcement on August 8, as did the rest of the world. Einstein was a great promoter of peace and a great admirer of Mahatma Gandhi. And after the Second World War, he had expressed his deep regret for having sent the letter to Roosevelt. Bodanis writes, this is a very beautiful book, E is equal to mc square. It is as if when God created the universe, he had said, I'm going to put X amount of energy in this universe of mine. I will let stars grow and explode. There will be fires, explosions of volcanoes. Despite all these variations, the total amount of energy will remain the same. So at t equal to 0, when the universe was created, God created a certain amount of energy. And that's it. And the rest is evolution. The amount I created at the beginning will not change. Energy will be converted to mass. There will not be 1 millionth part less than what was there to start. Oh, this one is good. This is also in the preface of Bodanis' book. A few years ago, I was reading an interview with the actress Cameron Diaz, very beautiful actress, in a movie magazine. At the end of the interview, At the end, the interviewer asked her if there was anything she wanted to know, and she said she wanted to know what E is equal to mc square means. So this is all for the young men sitting here. When your girlfriend asks you what is E equal to mc square, I hope you now know the answer. Now I go to the second paper. This is the paper for which he got the Nobel Prize. Not for his theory of relativity, not for his equation, not for his general theory of relativity. And he published in 1905 that radiation, that is light, can be emitted or absorbed only in discrete amounts called quanta. Quanta means that is known as the photon. Before that, Christian Huygens was put forward the wave theory of light. What is a wave? In order to understand, I'm sure all of you know that you take a calm pool of water and you have a tiny pin and make it move up and down, then circular ripples go out. And that is the wave, the propagation of a disturbance. And if you have a wave, if you have two pins, then each one will send out a wave. So if one produces a displacement like this, the other produces a displacement opposite, the total displacement will be zero. This is the manifestation of the phenomenon of interference and is a consequence of the principle of superposition. So you have two waves, they will produce interference pattern. But it was not observed. So therefore people did not believe in wave theory until Thomas Young performed this, one of the most brilliant experiments in physics. He took light, passed through a filter, allowed two pinholes, and these pinholes send out waves as if there are 2 point sources. They interfere to form this interference pattern. Once he saw that interference pattern, he was convinced that light was indeed a wave phenomenon. And light was allowed to pass through a narrow hole, and it therefore spreads around. This is known as the phenomenon of diffraction. And this could only happen if it is indeed a wave phenomenon. And these experiments were also performed. But then that light was a wave, was then very well established. But the question arose, and this is middle of 19th century or the early part of 19th century, how could it propagate through vacuum? And this is one of the most beautiful history which I would like all the young men and women to go through, but I do not have the time to go through the history. But eventually Maxwell synthesized the laws of electricity and magnetism, and he derived the wave equation. So understand what happened. Maxwell wrote down the Faraday's law, Ampere's law in the form of equations. He introduced the concept of displacement current, in which it says that a changing electric field will produce a changing magnetic field. That was Maxwell's only contribution. And using this concept, he derived the wave equation, predicted the existence of electromagnetic waves, calculated the velocity of the electromagnetic waves, showed that the velocity of the electromagnetic waves is close to the velocity of light, and that these two numbers cannot be accidentally equal. And with faith in rationality of nature, he said light must be an electromagnetic. And this is considered to be one of the greatest syntheses in the field of science, not in physics, in the field of science, that light and electricity and magnetism are part of the greater unification, that light is an electromagnetic wave. So around 1864, James Clerk Maxwell predicted the existence of electromagnetic waves and said that light itself is an electromagnetic wave. So oscillating, so you have a source of light or source of electromagnetic waves, there is a dancing electric field, the dancing electric field produces a magnetic field, the magnetic field produces an electric field. That is how the concept of fields were produced, as you all know, were introduced by Michael Faraday, which Maxwell used to understand the propagation of electromagnetic waves through free space. And as you know, right from gamma rays to radio waves, gamma rays, X-rays, ultraviolet, visible, infrared, they are all electromagnetic waves. They all travel with an identical velocity in vacuum. The only difference is that their frequencies are slightly different. And the visible portion of the spectrum occupies only a tiny portion of this electromagnetic wave. And with this concept, with the electromagnetic waves, as all of you are electrical engineers, all of you would know much more than myself, that it was so well established that people finally thought that they knew what light really was. So what light was, it was an electromagnetic wave of a particular frequency. So Max Planck had said, one of the great theoretical physicists, Maxwell's theory remains for all time one of the greatest triumphs of human intellectual endeavor. And then on the backdrop of this development, in his miracle year 1905, Einstein published an outstanding paper in which he proposed that radiation, that is light, can be emitted or absorbed only in discrete amounts called quanta. And then he introduced this equation easy. No one believed him. No one believed him. Even Max Planck did not believe him. Believe in the corpuscular model of that. This was a revolutionary concept and eventually led to the development of quantum theory. So this he explained. This is known as the photoelectric effect experiment, in which you have a metal plate, light was incident, and the electrons were emitted. The maximum kinetic energy of the electron was equal to the energy of the photon minus a constant which is determined by the metal. It was for this equation. This equation was experimentally verified by Millikan, and it was not for his concept of the light quantum, not for his theory of relativity, but it was for this equation that Einstein was given the 1921 Nobel Prize. So this was verified by Robert Millikan in between 1910 and 12 very accurately, and he said that this is known as the Einstein equation. This is the maximum kinetic energy of the emitted electron is equal to the energy of the photon minus a constant which depends on the, and he verified this formula with a tremendous degree of accuracy. And then in Arthur Compton shortly later did some beautiful scattering experiments, and he showed that the momentum of the photon is h nu by c, as I had mentioned earlier. This led to the question that is the photon or the electron a wave or a particle? If I ask you the question that is it a wave or a particle, the answer will be that is an incorrect answer. It is not both. It is neither. It's a very profound statement. That it is not that it is both a particle and a wave. It is neither a particle nor a wave. Then what is it? The answer is, I don't know. Not that I do not know, no one knows. Which led to quantum theory. So by then, 1897, I'll tell you what it is. I'll tell you, just hold on for a minute. So you have this, the electron was discovered by J.J. Thomson, and as you know, the mass of the electron is known to 9 decimal places. The charge of the electron is also known to 10 decimal places. It can be deflected by an electric field and by a magnetic field. So on the back of your mind, you think it is a tiny particle, which has a certain mass and a certain energy. But then it diffracts. It undergoes diffraction. So what is it? Is it a particle or a wave? It has both the properties. And the answer is, it is neither. Then what it is? It is described by the wave function psi. What is this psi? It is the solution of the Schrödinger equation. Understand the beautiful logic. So what is an electron or a proton or a neutron? It is described by the mathematical symbol psi. What is this psi? This is the solution of the Schrödinger equation. And where did this equation come from? It didn't come from anywhere. It came from the mind of Schrödinger. So Feynman writes, one of the greatest physicists of all time, where did we get that equation from? Where did we get that Schrödinger equation from? Nowhere. It is not possible to derive it from anything you know. It came out of the mind of Schrödinger. So in one slide, I have given you a tremendous amount of information. Maxwell, then in 1926, for which he got the Nobel Prize in 1954, Max Born said, mod psi squared d tau represents the probability of finding the electron in the volume element d tau. So therefore, you do this diffraction measurement. See this carefully. A photon beam or an electron beam or a proton beam comes in and it undergoes diffraction. That is, it spreads out, as I had shown earlier. This is the intensity pattern that you work out in your BSc class. what quantum theory gives us, if you solve the Schrodinger equation, it gives us a probability of the momentum, the x component of momentum lying between px and px plus dpx is given by the same formula. So where will it arrive? No one can predict. Physics has become, with the advent of quantum theory, a probabilistic theory. Classical physics is a deterministic theory. Quantum physics is a probabilistic theory. Where will it arrive? I do not know. I can only give you a probability distribution. How do I get the probability distribution? By solving the Schrodinger equation. So this is the beautiful interference. Just spend 2 minutes on this. And I think this will make you understand what an electron is. The electron produces this interference pattern. And that interference pattern is possible only if it is a wave. So therefore, electron is described by a wave function which is at psi1 and S1 and S2. That is, it passes through both the hole at once. It is not the splitting of the electron into half and half, because when you make a measurement, it is either the whole electron or the zero electron. You cannot ever measure 1/3 of an electron or half of an electron. So to explain this intensity distribution, so this experiment this is the top photograph, corresponds to 10 electrons. And as you increase the number of electrons, slowly the interference pattern emerges. So you can say that the probability of the arrival of this electron is here, is small in this region. Probability is large here. So therefore, as the electron wave propagates, it is described by a wave function which is everywhere. So it is everywhere, and the process of measurement makes it collapse to one point. And the theory gives the probability distribution for that. Where will the detector detect? No one can predict. I'll give you one more example. So here there is an electron wave packet, one single electron described by a wave packet reaching a potential barrier. So it can be reflected, as you can see with the glass plate. You can see your own image, whereas on the other side person can see you. So therefore the light that is emitted from my face is reflected as well as transmitted. So here the electron is partially reflected and partially transmitted. This is what my Schrodinger's wave theory tells us. Wave equation. So it is here as well as here. This can be hundreds of kilometers apart or thousands of. When you make a measurement, then it is either here or there. So it is described by a wave function which is present in both the holes. So this is the picture of a young girl, and see this picture. Each spot, this is the photograph corresponding to 3000 photons, and this is corresponding to 28 million photons. So the probability in this region is large. Probability of arrival in this region is extremely small. Where will an individual photon arrive? No one can predict. Each point is one photon, never half of a photon. Quantum theory gives us the probability distribution. So if there are very small number of photons, where they will arrive, I do not know. But if there are a large number of photons, slowly the image will appear, as predicted by the classical theory. And these interference experiments have been carried out with fullerene molecule. Fullerene molecule consists of 60 carbon atoms. That is the mini soccer ball. And these are some of the most beautiful experiments that have been recently described. And so therefore, if you ask me the question, what is a fullerene molecule? Is it a particle or a wave? No, it is neither a particle nor a wave. It is described by the Schrodinger's wave function psi, which is the solution of the Schrodinger equation. And you get this beautiful interference pattern. So I will describe you one more experiment, and that is, if you have a beam splitter, a partially reflecting plate, and if you allow light beam to pass through, 100-watt light bulb. So you say half of the light will go here, half of the light will go here. Now you go to the corpuscular model of the radiation, that it is individual photons. You have now light sources which sends out individual photons. So you ask yourself, will it go here or will it go here? You say 50% of the time it will go here, 50% of the time it will. No. When it arrives at the beam splitter, it is in the reflected beam as well as in the transmitted beam. If you make a measurement, then it is either here or there. Before you make the measurement, it is here as well as there. So you carry out the following experiment. You have a light source which sends out equal photon, and beam splitter reflects 50% of light. So whenever the detector D1 records, you detect 1. Whenever the detector D2 records, you detect 0. Which photon will go where, you cannot predict. And so thereby you generate a set of completely random numbers. This is the basic principle on which the quantum random number generator works. It will never repeat itself. Any algorithm will repeat random numbers after a while. So because of indeterministic nature of quantum mechanics, we can generate true random numbers. Such a device is known as a quantum random number generator. So you use any algorithm, then after say trillion numbers or a billion numbers, it will repeat itself. Not with the quantum random number generator. And so therefore this has given the experimentalist, a computer scientist, a great opportunity to work with true random numbers. Quantum mechanics, Einstein told to Niels Bohr that quantum mechanics is certainly imposing, but an inner voice tells me that it is not yet the real thing. I am at any rate convinced that God does not play dice. He always believed in a deterministic theory. And so he never believed, although he was the main person who led to quantum theory, he never believed in quantum theory. Much later, in September 1944, when Einstein was about 65 years old, Einstein wrote to Max Born, even the great success of quantum theory does not make me believe in the fundamental dice game, although I am well aware that our younger colleagues interpret this as a consequence of senility. Then there are entangled photons, which is a consequence of what is now known as the EPR paradox, that one atom, calcium atom, emits two photons of orthogonal polarizations. But they are not always orthogonal like this. If this is X, this is Y. If this is Y, then this is X. If this is X prime, then this is at right angles to that. So now, these two photons are said to be entangled photons. And these two photons can be billions of kilometers apart. Now, you make a measurement of one. Then this photon collapses to a state which is perpendicular. So Einstein said that this is an incompleteness of quantum theory. But this has now, because you cannot make a measurement on one particle which is billion kilometers away, and this sends a signal here instantaneously. That is not possible. But recent experiments have proved that entangled photons do exist, and measurements do prove that if you make a measurement on this photon at t equals to, immediately this collapses to a state of horizontal polarization. Chalo, this could be. Feynman said, I think I can safely say that nobody understands quantum mechanics. So, in last few minutes, I will just briefly describe what is the theory of relativity. Theory of relativity is, let us suppose I have a laser pointer. Okay. I am in a train, the same train where I was before. The train is moving in this direction with a velocity, let us suppose 100 kilometers per hour. 100 kilometers per hour. I have a tennis ball in my hand. ठीक है अंशु? समझ में आ रहा है? I have a tennis ball in my hand. I roll that tennis ball with a velocity 50 kilometers per hour. So you will say, who is standing on the platform, that the tennis ball is moving with a velocity 150 kilometers per hour. ठीक है? No cheating. Okay, I am in the train. I am moving with the train at a velocity 100 kilometers per hour. I have a tennis or a cricket ball in my hand. Along the length of the train, I roll the ball with a velocity of 50 kilometers per hour. Then you will say that the tennis ball is moving away from you with a velocity, because I have imparted that 100 kilometers to start with, plus 50, so it is 100. It is moving with respect to me with a velocity 50 kilometers per hour. So with respect to you, it will move with a velocity of 150 kilometers per hour. What Einstein said was that you have a laser pointer, you switch it on and switch it off, and you produce what is a light pulse or a light bullet. Okay? I am still inside the moving train. I am holding a light a laser pointer, I switch it on and switch it off and produce a light bullet. And that light bullet moves away from me with a velocity of 300,000 kilometers per second. And this was the only new thing that he introduced in the 1905 paper. He said that light with respect to you will also move with the same velocity. The constancy of this velocity of light. That is the only statement that he made if you read the original paper, which is now available on the internet, that constancy of the velocity of light. So in this paper, he said that light always propagates in free space with a definite velocity that is independent of the state of motion of the emitting body. Okay? It is something like this. It is something like this. The consequence of this, that is suppose a train is moving away from you with a velocity, say, 20 kilometers per hour, and you are running behind him with a velocity, say, 19 kilometers per hour. Then you will feel that the train is only moving with a velocity of only 1 kilometer per hour. For example, if there is a train beside you and you are also moving, he is also moving, but he is moving slightly faster, then you will see that it is almost stationary. But if there is a light beam, and then suppose you are running chasing the light beam, with the light beam for me and him, we will be moving away with respect to him also with the same velocity. That is the constancy of the velocity of light. And see the consequence of it. Understand this. Focus. That I now put the laser pointer in the vertical direction. Okay? I now put the laser pointer in the vertical. I switch it on and switch it off. Produce a light pulse. And on top of my ceiling, there is a mirror. So the light pulse goes up and comes down. There are two events. Production of the light pulse and the detection of the light pulse. And there is a time interval between them. Let us suppose it is 1 nanosecond. Going up and going down. Okay? I see that there is a time difference of, let us say, 1 second between the two. Now for you, what will happen is, you switch on to the light pulse, I am here. By the time it goes to the mirror is here. By the time it comes back, it is here. So you will see that the light takes a triangular path. Einstein said the velocity is the same. It takes a larger path. Slightly longer. And that is one of the greatest statements made by many scientists, that time is not absolute. And that is what he wrote to his friend Michel Besseau, that time is not absolute. So my watch and your watch will be slightly different. So you see, it is something like this. Let us suppose, I am 70-year-old and you are, say, 20-year-old. Something like that. 15 years, 20 years. You are 50 years young. I can go to a distant star. I will come back and I will be only 80 years old and he can be 85. So today he is younger to me, but tomorrow I can be. That is the consequence of specialty. So I told you the basic things and the basic algebra, and it has been verified by numerous experiments. So this is the experiment. I have a light bulb, I put it on and put it off, the time difference between the two events. What are the two events? Production of the light pulse and the detection of the light. This is 2h by c, and for you who is sitting, it will take a triangular path, so it will be slightly longer. So therefore, the time interval between the two events occurring at the same place, which is known as the proper time, is slightly less than the time interval between that you measure. But since the velocity of a person is usually much small compared to the velocity of light, so the time differences are extremely small. So Einstein told his friend Besseau that time is not absolute. And this has been now verified in experiments, and that I wanted to tell you that experiment, this using new mesons, you can read, since the time is up, I will just shorten this discussion. This experiment was suggested by none other than Homi Bhabha, who is the founder of nuclear. Homi Bhabha, in a paper published in Nature 1938, was the first to point out that the measured lifetime of meson and flight is affected by time dilation. Chalo. So it is something like this. There are twins. He enters a spacecraft and goes to the nearest star and comes back. He thinks he has spent 1 year and the person on the ground has spent 10 years. No object, this is the consequence of special theory of relativity. No signal, no influence can travel any faster than the speed of light. But there are, इसका consequences देखिए. Special theory of relativity के philosophical consequences. That no signal can travel with a velocity greater than that of light. So there is a star, let us suppose 10 light years away, and there is a planet surrounding that, and there is life there. So there is a volcano. So the argument goes like this, that God is one. Whether you are a Hindu or a Muslim or a Christian or whatever, God is one. So let us suppose he is here today. He is here today. So then some event occurs at a near planet or a nearby star, and special theory of relativity tells us that it will take at least 10 years for the information to come in. So if God is here, then he cannot do anything there until after about 20 years. 10 years to receive the information, 10 years to receive. And you will say, God is everywhere. But if God is everywhere, then he can tell me right now what is happening in that planet. But that is impossible. So he is here as well as there. Then he can tell me what is happening right now. That means he can send signals with a velocity greater than that of light. That is impossible. So God cannot. So after the theory of relativity was given, so all hell might be breaking loose 10 light years away, which is mere stone's throw in interstellar space, and the bad news would at least take 10 years to reach her. And then it would take another 10 years at least before the God, could do anything about it. You may say that this is terribly naive, that God exists everywhere. Perhaps so. But that reality comes to the same thing as saying her thoughts and her influence can travel at infinite velocity. But that will violate the special theory of relativity. So I conclude by saying, Einstein was many times asked, do you believe in God? Do you believe in God? And his answer was that he sees the structure in this world. There must be a creator. And therefore, he says, there must be a creator and there must be a God who created this. But then he makes one of the most profound statements. And he said, but I do not believe in God of theology, which rewards the good and punishes the evil. Hear this once again. I do not believe in God of theology, which rewards the good and punishes the evil. And why did he say that? Why did he say that? I'll tell you. So on several occasions, Einstein was asked, do you believe in God? He says, the famous example that he gave was, in his autobiography, he says, we are like small children in front of a huge library. The library is stacked with books of different languages, beautifully stacked and arranged. Someone has written them. Someone has arranged them. I do not know. We can only read. We can only see what he has written, what he has written. Okay? So, do you believe in God? Einstein said, we read this carefully. My religiosity consists of a humble admiration of the infinitely superior spirit that reveals itself in the little that we can comprehend about the knowable world. So beautiful. You see this bird, the beautiful manifestation of different colors. Not in one bird, thousands of birds like that. Someone has designed it. You see our own body, 2 eyes, 2 legs and this thing. And so beautifully designed, of which we understand only very little. So someone has created it, and that is God. You see this fish, all fish have the same beautiful projection of colors. Someone has designed it. But then he says, I do not believe in the fear of life, in the fear of death, in blind faith. I believe Spinoza was one of the greatest philosophers of all times. I believe in Spinoza's God, who reveals himself in the orderly harmony of what exists, not in a God of theology who rewards good and punishes evil. And why did he say that? he saw in front of his eyes, this is an 8-year-old boy taken to a concentration camp. For what fault? Then he says, is God seeing that? Then he sees, then you must have read the book Diary of Anne Frank. She was taken to the Auschwitz concentration camp, which is in Poland. I have seen that myself. In 1964, when I was returning from the United States, I saw that. And the thing that is written on front is that work, freedom by work. And if you go inside, that one human being can do to another human being is unimaginable. And you do to another human being who you do not know, who may be differing from you only in religion. And not one, not two, not 100, not thousands, hundreds of thousands were killed. And the question that he asked was God watching them? So as I was telling little before, that even Sri Ramakrishna had said that if you walk in a dark jungle which is infested with animals and snakes and other things, and if you say that Ishwar meri raksha karega, तो तुम मूर्ख हो. ईश्वर तुम्हारी रक्षा नहीं करेगा. तुमको खुद की रक्षा खुद को करना पड़ेगा. You have to protect yourself. God will not protect you. And therefore he said, I do not believe in God of theology, which rewards the good and punishes the evil. Steve Jobs took this magazine. This is the cover magazine of Life magazine, July 1968. Starving children, not hundreds, not thousands, hundreds of thousands of children died in late 60s in Biafra. And he took this magazine to the pastor of the church and he says, does God know about this and what is going to happen to these children? He said, I think different religions are different doors to the same house. Sometimes I think that the house exists, sometimes I do not. It is the greatest mystery. Mahatma Gandhi had said, I worship God as truth only. I have not yet found him, but I am seeking after him. But the best that I found was by Anna Hazare. He says, I do not believe praying to any God in a temple. Read this, beautiful. I do not believe praying to any God in a temple, but instead seek it in helping the poor, needy and sick. Chalo. In the last phase, then his deathbed, April 1955, when he was about 77-year-old, Einstein refused surgery and said, it is tasteless to prolong life artificially. I have done my share, it is time to go. I will do it elegantly. His stepdaughter wrote to Mrs. Max Born, read this, I did not recognize him, that is Einstein, at first. He was so changed by the pain and blood deficiency. But his personality was the same as ever. He joked with me and was completely in command of himself with regard to his condition. He spoke with profound serenity, even with a touch of humor, about the doctors and awaited his end as an imminent natural phenomenon. We all have to learn this. And awaited his end as an imminent natural phenomenon. And she writes, as fearless as he had been all his life, so he faced death humbly and quietly. He left this world without sentimentality or regrets. How do I conclude this talk? So I thought I will show you a few of the cartoons and slides. This is for a person like me. Life, when you get old, your children say that don't work so much. But life is like riding a bicycle. To keep your balance, you must keep moving. Anil, do you agree? Yes. Then this is how he arrived at the equation E is equal to mc square. This is and then but this I do not agree. This is Steve Harris. Albert Einstein in his later years was unable to figure out why, if he was so smart and so famous, he wasn't rich. But that is because of his own. He could have been. Oh, the answer is he could have been rich, but he did not want to be rich. That is the most important thing. And then, in spite of knowing everything, he says, this slide I have not shown to my wife. year was 1939. The year was 1939. India was celebrating the 70th birthday of Mahatma Gandhi. India was celebrating the 70th birthday of Mahatma Gandhi. Einstein was a great admirer of Mahatma Gandhi. So he wrote the following about Gandhi. Read this. Most of us have forgotten Gandhi. A man of wisdom and humility, armed with resolve and inflexible consistency, who has devoted all his strength to the uplifting of his people and the betterment of their lot, a man who has confronted the brutality of Europe with the dignity of the simple human being, and thus at all times risen superior. And then he says, generations to come will scarce believe that such a person as Gandhi, ever in flesh and blood, walked upon this earth. So I would like to conclude this lecture by saying, generations to come will scarce believe that such a person as Einstein, ever in flesh and blood, walked upon this earth. These are the two references. This is a letter that Satyendranath Bose wrote. Oh, you must please. Satyendranath Bose published a paper in 1924, wrote a paper. He wrote to Einstein in his own hand on 4th of June 1924 when he was at Dhaka University. The paper was not accepted by Philmag, a magazine in UK, and then Einstein saw the importance of the paper and he translated by his own hand on 3rd July 1924. I thought I will show you. He translated and he published it in Zeitschrift for Physics. I hope all of you have heard the name. And then, record karna. So then, after independence, Jawaharlal Nehru went to meet, he went for a United Nations meeting and he went to meet Einstein. And guess what was his first question? This is what I have read. How is Bose? And he thought he was asking him about Subhash Chandra Bose. Then he said, no, I was asking about Satyendranath Bose. He did not know who was Satyendranath Bose. But the greatness in Nehru was that when he came back, he immediately made Satyendranath Bose as a national professor. And you know, my father was from Allahabad University and he knew Satyendranath. We had the opportunity of hosting him in our house, this great man, with his family, because we were in Agra. So we had many guests. Remarkably simple man. He should have got the Nobel Prize. But I had not seen a person of such great simplicity and wisdom. I remember him only very little because I was very young at that time. And he had also had very interesting discussions with Rabindranath Tagore. There's a very beautiful book by Amiya Chakravarti which describes their philosophical conversation. This is his first wife with whom he was very passionately in love before his wedding. Then the marriage got sour and then he flirted around with, these are his two children who became very well known person, and this is his second son. And in 1933 he was admitted to a mental hospital. And the amazing thing is that between 1933 and 1955 he visited him only once. So he had a very dual personality. He had tremendous compassion for the poor and the downtrodden, but at the same time extremely strained relations with his own family. This is his second wife, and even then he had numerous women with whom he used to go around with. That the story goes.